Welcome to Module 1.3, where we'll learn how DApps work, how their backend works via smart contracts, and how the frontend and backend interact with each other. Let's start by describing the DApps experience from a user's perspective. DApps may seem complex, but are in fact very easy to use once you have the right tools in place. You'll just need a compatible wallet like MetaMask or Trust Wallet and some cryptocurrencies to start exploring the thrilling world of DApps. The user interface of DApps is generally simple and familiar to users who are used to using traditional apps. DApps can be mobile apps or websites, because a DApps frontend uses the same programming languages as centralized applications, such as HTML or JavaScript. DApp developers also use similar web tools, libraries, and frameworks to create user interfaces that are comparable to that of centralized applications. What makes DApps unique is their backend, smart contracts, which are decentralized computer programs on the blockchain that run automatically when preset conditions are met. In essence, if condition A is satisfied, then action B is triggered automatically by the smart contract. Smart contracts achieve numerous objectives, including trustworthiness and transparency, as all parties can trust the outcome without relying on a third party, and are able to see the terms of the smart contract on-chain with complete transparency. As blockchain technology offers strong encryption techniques, it ensures that the terms of the contract cannot be altered once set. Moreover, the automation process can reduce the time it takes to complete transactions, providing higher efficiency. By eliminating or reducing the need for intermediaries, smart contracts can also reduce costs. Lastly, smart contracts can minimize the risk of human error. One thing to note, however, is that once a smart contract is deployed, nobody can modify it in any way. If there are any errors or weaknesses in a smart contract, it can only be deleted. This can have devastating consequences, especially if there are funds stored in the smart contract. That's why blockchain projects have to perform vigorous audits to try to ensure the smart contract does exactly what they need it to do. Having delved into the backend of a DApp, let's explore how this backend interacts with the front end. Smart contracts are typically connected to their front end through tools known as client-side libraries. Users rely on crypto wallets to access and interact with DApps securely, as the wallets serve as the user's gateway to the blockchain and store the user's private keys, which are needed to sign transactions and interact with smart contracts. Once the smart contracts and the user interface are established, DApps need a mechanism to conduct transactions on the blockchain and retrieve data stored on it. To achieve this, they rely on nodes, which are participants in the blockchain network responsible for maintaining and updating the distributed ledger. Developers can either establish their own nodes or utilize third-party services, commonly referred to as providers. Many DApps opt to use providers to manage nodes, because it's often more convenient and cost-effective than setting up and maintaining their own nodes. However, this introduces a degree of centralization to the DApp. If a DApp is solely reliant on a single provider and that provider experiences issues, the DApp's functionality could be compromised. Nodes are just one component essential for a DApp's operation. DApp developers also need to address data storage. Given that storing or processing voluminous data on-chain can be expensive, many DApps utilize off-chain data storage solutions for information that doesn't need to reside on the blockchain. These off-chain storage solutions range from centralized data services to decentralized peer-to-peer storage platforms like IPFS and Ethereum's Swarm. By now, it's evident that elements within a DApp aren't always fully decentralized. Developers face choices regarding the degree of decentralization they want to achieve for their DApp. Each decision carries its own advantages and drawbacks, weighing factors like cost and efficiency against the desired level of decentralization. Now that we've explored the various components that make up a DApp, it's crucial to also discuss the Ethereum virtual machine, commonly referred to as the EVM. The EVM is the computational engine responsible for deploying and executing smart contracts on the Ethereum network. It determines the state for each new block added to the Ethereum blockchain. In essence, the EVM can be envisioned as a distributed computing environment where smart contracts and DApps come to life. One notable feature of the EVM is its potential to boost interoperability among DApps. Several blockchain networks, including BNB Chain and Avalanche, have designed their systems to be EVM compatible. This compatibility implies that, with some adjustments, smart contracts developed for Ethereum can be deployed on these EVM-compatible blockchains. This brings about advantages like improved interoperability and potentially reduced development costs. While DApps offer numerous benefits, they aren't without associated costs. To account for the computational resources used during operations on the Ethereum network, users must pay gas fees. These fees are settled in Ethereum's native currency, Ether, but are quoted in a smaller denomination called Gwei. For perspective, 1 Ether is equivalent to 1 billion Gwei. Much like its name suggests, gas can be likened to the fuel that powers the Ethereum network. Just like how gasoline propels a car, gas fees are influenced by various factors, including gas limits and base fees. Traditionally, Ethereum utilized an auction mechanism to determine these fees, but with the introduction of EIP 1559 and other updates, the fee mechanism is evolving. It's a multifaceted system that can change as Ethereum continues to develop. In the next module, let's examine different types of DApps, as well as the opportunities and limitations of DApps.